on technology with 4 great speakers. We're going to have 15 minutes each with Q&A sessions, so hopefully we won't go longer than the 1 hour we have allocated for this session. We're going to have 4 presenters today, and the session will be presenting on the advancements in technology for infrastructure monitoring and management. Dr. Ozer is going to start with a discussion on automated construction quality monitoring using uncrewed aerial vehicles, followed by Mr. Bill Prieto, who will present on insights on the necessary infrastructure adjustments to accommodate automated trucks and platoons. Then Dr. Elam will then introduce a smart Internet of Things-based systems for remotely detecting earth movement in highway embankments. And finally, Dr. Congress, who will be present on UAV-based asset management for bridges incorporating machine learning models. So it's going to be an exciting section here. And I'm going to go, we do have now getting more attendees. We're going to go with our first presentation with Dr. Hasen Ozer. Dr. Ozer is my colleague and an associate professor in the School of Sustainable Engineering and the Built Environment. His research focuses on pavement material characterization, pavement design and analysis, and the development of rehabilitation and preservation programs. Dr. Ozer develops computational mechanics methods for structural performance, modeling of pavements, and uses life cycle assessment tools for advancing sustainable transportation infrastructure. Thank you, Hasan, for being here. The floor is yours.
Thank you so much. It's a great pleasure, having this presentation in the inaugural colloquium, and great pleasure to be part of this team. And I will be talking about this project about using drones in assisting construction quality for asphalt pavements. And my students, Naga and Missy, they are the ones that basically are doing the great work, and I'm taking sometimes the credit for making such presentations and events. So if you can move forward with the next slide, I can introduce the background for the study and then move on to the things that we have done in the past using the Insight funds. So the asphalt pavement construction quality is really extremely important, and it's an essential part of building long-lasting pavements. And one of those really components of the quality is achieving the density. And these are traditionally done using conventional methods such as spot checks by taking cores, or using density equipment such as the one that you're seeing on the picture, nuclear gauge density equipment. But these are just spot checks to just make sure that the construction is done properly, but that doesn't really give an idea about the entire pavement section. And if you can move on to the next slide. And recently, there are some advanced techniques being developed. And one of those is that you're seeing in the slide is this paver-mounted thermal profilers. This really is not intended to give the density directly, but it's really an important part of the construction quality is the temperature. So this type of really profilers, when they are mounted on the pavers, and sometimes they are also mounted on the rollers, they can really give an idea about the temperature profile of the pavement or the mud as they are being paved. And the mud temperature is really critical to achieve the density. It's one part of the equation. And these sensors give us an idea about how uniform the temperatures are, and whether there are some anomalies in the temperature distribution on the surface of the pavement. These are extremely important, again, to achieve quality in the construction of pavements. If you can go to the next slide, please. And then the techniques continued their evolution. And then this is, for example, the intelligent compaction. Now, this is a package that includes the profilers, temperature profilers, but in addition to the temperature profilers, intelligent compaction technology includes some sensors inserted and added to the rollers to basically monitor the stiffness evolution, the stiffness or density evolution. So these rollers can be GPS tracked and heavily sensor equipped. So that way, at every pass, they can get an idea about how the density is evolving during the construction. So this is really a package now, intelligent compaction package. When they are combined with the thermal profiler, that can really give us a good idea about how really much quality is being achieved at each construction site. And one of the, of course, drawbacks of those systems is they're relatively more expensive. They're not being used in every project because of the cost, and then usually the contractors use this some for special jobs, such as the one that I visited last week. There is a racetrack construction going on. It's a very special operation, and the contractor chose to use this system because that was a special requirement for that particular job. And our idea was, if you go to next slide, please. Our idea was, can we utilize drones to assist in this process? And if you think about the key variables of the construction quality or achieving density, is the temperature and rolling operation. And drones can really give us a good idea about both of these basically variables. If you can track the temperature using a drone, and if you can track the roller movements using these aerial pictures, can we really get an idea about how well we are really going to be achieving density and uniformly. So that was basically the problem statement that we had in this project that we tackled over the last 2 years. Next slide, please. And this is highlight. This is our system is consisting of a DJI drone, and then equipped with thermal sensors, an infrared sensor that you're seeing on the picture on the left. And then this is a picture, for example, we took in a job site in Arizona area, Phoenix metro area. It shows the recently paved asphalt pavement, but it's also surroundings. You can see, we can capture the temperature profile of not just the pavement, but everything else around the pavements. And those thermal images can be processed to give basically an idea about how well the construction is going. And also thermal images are collected with these 2 seconds interval for the roller movement tracking. Next slide, please. And our system, when it's really completed, this is our future goal. We are not there completely yet, but our idea is, if we have this UAV assisted data collection system protocol, which we are working on as part of this project at Ensite, and then we can control the mud temperature, monitor monitor the mud temperature, and look at the anomalies, how uniform we are really getting the temperature to really achieve the density. And then we can really develop temperature profiles, not only just on the surface, but within the depth of the pavement. And then we can look at the things, for example, in the entire mud, how much or how well we are achieving the density. And our goal is to provide near real-time feedback to the contractor. If something happens, for example, at the job site, if they're not really getting higher efficiency with their operations, they can make necessary corrections on the spot. That's our ultimate goal. We're not there yet, obviously, but we're developing the components to reach this goal. Next slide, please. And for that development, we visited many job sites in the Phoenix metro area. So far, we visited 14 paving jobs around Phoenix area. And this is the perfect season for us to go and then collect some data. And then we still are, we continue visiting job sites until the construction is over in Arizona. Usually contractors takes a break in December and then early part of January, and as soon as the weather warms up in February, they start paving. So we are still collecting data from the job sites. And this is, for example, showing our operation, our students, our team collecting the data by using our drone. Next slide, please. And those are some sample thermal images collected from various test sites. And we really have done majority of our observation in the residential areas. And it's relatively easier to use the drone. And you can see the RGB images and the thermal images collected from the same site. We have collection of those images for data processing. Next slide, please. And our processing protocol is explained in this slide. We start collecting those thermal images, what we call IR images that you see on the left-hand side of slide, and that really gives us the surface temperature. In this particular example, for example, you can see the temperatures from 150 to 115, and because I think the paver was on the top of this picture, and there's really the paver moves on and the mat cools down. So we look at those images. First is to look at for the anomalies. Are there any non-uniformities in the temperature profile? You can see, for example, in here there are some degree of anomalies annotated in this graph. If you have too much differences in really neighboring, for example, segments on the pavement, that receives a different index. If everything is perfectly uniform, then you get a very good index. So we can really have a plot that looks like this on the spot that shows basically how uniform the temperature was on the surface of the mud. But we also use the same image to track the roller. And this system now is recently developed by using a machine learning model and then using some available machine learning models. And then we adapted that model to detect the rollers. And then we use the object tracking algorithms developed in YOLO. You look at one system, and then we track the roller, and then we quantify its movements to understand how efficient the movements are to really achieve the density. And then we can get the accumulated roller passes and the average roller speed. These are really the key properties that can really be influencing the density. Next slide, please. These are some initial findings from our studies, from our early test site visits. This slide shows, for example, the temperature data collected on the mat as a function of time. And the reason why we have a metrics like this, because we have really been collecting data for about 60 minutes. So you can see there's a lot of red, different colored boxes or cells that indicates there are some significant differences in between neighboring areas, segments. But then if you really continue taking those measurements, those basically alarms or those red flags are disappearing. So that means you may have some initial anomalies, appearing on the pavement when it's really hot, but those anomalies can be corrected over the time. And that's one of the benefits of the drone is it's not just only looking at behind the paver, but it's looking at the entire mat, even if the paver really moves on to different sections in the construction site. Next slide, please. And these are interesting findings from some of our test sites. This, for example, the picture on the left, that shows something that we know very well in the industry, and it's a longitudinal segregation. The dark spots indicate the colder areas, and the brighter spots indicate the hotter areas. And you can clearly see in the center of the pavement, there's a dark spot. And we also know why that dark spot formed in this particular test site. It's a typical paver configuration, and that paver configuration in some circumstances can result in such cold spots, and those cold spots eventually, of course, lead to some density variations. And then we see sometimes in our pavements those longitudinal cracks right in the middle of the lane, and that's not really related to loading, that's not related to temperature, that's primarily related to construction quality. So we can observe such things using our system. Another, for example, anomaly we observed is that you can see a dark spot appearing in the middle of the picture, and that dark spot is because the paver stops waiting for the next truck to basically deliver the hot mix asphalt, and that's basically material inside the paver used when the new basically load comes. But that material, of course, cools down, and they put that material on the pavement. You can see clearly those dark, basically cold spots as they move on. Next slide, please. And this is some updates from our recently developed roller tracking protocol. And we're using object detection methods to keep track of the roller. And you can see on the animated pictures on the right, the roller movements. And then each one of those roller movements are mapped into different types of pictures, different types of analysis. And you can see the roller passes, the number of passes each basically cell receives, and average roller speed, that's also quantified. And at the end, for example, the very right picture, you can clearly see how much of those areas are not really efficiently compacted. So if you can see the numbers 12 all the way to 0, and then we are really trying to go, let's say, 8 or 10 number of passes at every cell, but there are some areas clearly that didn't receive enough compaction. So that will literally give us an idea about that, give a good feedback to the contractor to work on some of those areas that they are not really efficiently compacting. Next slide, please. And at the end of the day, our deliverables, research deliverable, to sum it up, is our goal is to identify and quantify thermal non-uniformities and analyze roller movements to determine the roller passes and speed, because we believe these two are really critical to achieve density. And if there's something wrong in either one of them or both of them, it's great. It's likely that the target densities will not be achieved uniformly. And our goal is to estimate the density. It's not a direct estimation, but we're hoping to get an idea about whether the contractor will achieve the uniform density using these measurements. And our goal is to provide near real-time feedback to the contractor so they can take corrective actions on the spot. And we think that this can be a cost-effective solution that can complement the IC systems in the marketplace. Next slide, please. And our ongoing work is we still have some work to do with the roller detection algorithm, because the last test site that we visited, they were using 3 pavers, number of rollers, multiple lanes being constructed at the same time. That's a special operation. So our algorithm needs to capture basically multiple rollers working on a large width mat construction site. So that's something that we are working on to make sure that we can capture multiple more than one rollers, and then monitor its movements. And then we want to really convert the parameters, our output, to actually deliver. But there's an actual specifications for temperature profiling. And then we are trying to convert our outcomes, our output also, to be compatible with the AASHTO, and then correlate our, of course, readings with multiple test sites to develop our density model. And with that, I think this is probably my last slide. And then in the next slide, you will see some QR codes for our published work and ongoing project details. And thank you for listening. And I'm not sure if we have the Q&A at this point, or we're waiting until the end of the session, but I'm happy to answer if you have any questions.
Thank you so much, Hasan. Appreciate it. Very nice and interesting. I think the Q&A session is going to go right after each of the speakers, so we got a fresh mind here. Fortunately, we don't have just 1 minute or for one quick question. We're running behind. Does anybody has any question for Hasan? Well, I do have one. It's related to the challenges, right? The challenge that need to be addressed. You've been working on that for a while, and I can imagine so many regulatory and technical challenges. What do you consider to be the more prevalent or the most important challenges, whether technical or regulatory or even ethical?
With the drones, the biggest challenge, of course, you cannot fly drone everywhere. You need to get some special permits in some areas, especially if you're close to the airport. But that doesn't mean that you cannot fly. You just have to apply for the permit to get that basically drone to be used at the site if it's closer to the if it's closer to the airport, FAA regulations. And so that's one of the biggest challenges. And operating the drone, of course, there are some risks operating the drone. Accidents can happen, and that's a big health and safety risk. That's one of my nightmares. And that's why the drone operators are trained. They are official pilots, and whoever is operating our drone, they really go through a rigorous training, and they become official pilots after they really get the certificate. So we don't let our drones being used by everybody. That's probably one of the future challenges, to see if this really rolls into practice. Who is going to be responsible for using the drone at the job site?
All right. Thank you very much, Hasan. I don't see any more questions on the Q&A, or just speak up. Right. If not, I thank you so much for your great presentation. I appreciate that.
Thank you.
Right. Moving on, we're gonna have next Mr. Bill Prieto. He is an associate transportation research with the investment analysis program of the Texas A&M Transportation Institute. Before joining in 2019, Mr. Prieto earned his Bachelor of Science in Chemistry degree from the University of North Texas, where he researched surface catalysts for converting biomass into fuel. He went on to his Master's of Public Administration degree from the George Bush School of Government and Public Service at Texas A&M, and his studies at the Bush School followed the policy analysis track with a concentration in energy and environmental policy. Since joining TTI, Mr. Prieto has focused on policy analysis, transportation finance, data visualization, covering topics like funding programs, autonomous tech, urban air mobility, and alternative fuels. So we welcome you to this podium and appreciate your involvement today. Go ahead,
Yeah,
Bill. Thank you.
thank you for having me. Let me share my screen.
So we have a little time here. Camera off.
All right. Can you guys see my presentation before I get started?
Yes, sir. You're good to go.
Nice. All right, so I'm going to talk to you guys today about the necessary infrastructure accommodations for automated trucks and truck platoons. Curtis Morgan is the PI of the project, but unfortunately he wasn't able to present today, so I'm going to be presenting in his stead. So the objective of the project is to obtain a clear understanding of key topics, including the infrastructure needed to adopt autonomous trucking and truck platooning, as well as an updated status of the industry. And so to achieve this goal, we developed a survey to gather information on infrastructure needs, challenges, solutions, economics, and policy. And for the project scope, we broke down the project into the following. So we have a literature review. We identified a couple of survey participants. We developed a survey. We're in the process of analyzing the survey results. And after that, we're going to hold like a peer exchange or workshop or interviews, depending on availability. And then the final deliverable will be a set of best practices and recommendations in the form of a final report. So, for the literature review, it's a mix of sources, including journals, reports, and news articles. And what's interesting about this topic in particular is that it's very new and things keep constantly changing. So this is more like a living document. So every week we're like checking online articles to see if there's if there hasn't been, or if there have been any new developments. And for the literature review, we focused on searching the autonomous truck composition or technology that's still emerging for the autonomous trucks. We also looked at truck platooning and the application for that, but there's still limited information on that. We looked at commercial companies that focus on autonomous trucks or control systems for third-party freight loads. We looked at trends in adoption, and we also reviewed recent industry developments. And so here's just like an overview of what an autonomous truck is comprised of or equipped with. So it has like the LiDAR, the camera, radar, and communication capabilities. And for this, we looked at several autonomous truck companies, and these seem to be like the major equipment factors that they had on there, and to kind of register its surroundings. So the communication capabilities, that includes anything from like cell towers to your radars and your cameras, and who knows, they might have other proprietary stuff that they don't want to publish. And here's an idea of what a platooning scenario could look like. This is from one of our previous studies. And for this, it's split up into a midterm and a long-term scenario, where in the midterm, you still have a driver in the lead vehicle, but the truck that's platooning with it is driven autonomously. And for this, they still have to follow the hours of service regulation. So that means taking a 30-minute break, and then also like a 10-minute break. And hitting the transport ports to switch the autonomous driven truck to a person that's driven the truck manually for that last leg. In the longer term, the whole trip is going to be driven autonomously. So once it exits the factory or a distribution center, it'll be driven autonomously all the way to its end point. And so for this, there's more fuel savings, and there are no hours of service regulations. So the expectation is that things will deliver at a more efficient pace. Onto infrastructure, which is the meat of the project. We learned that an industry is referred to as the operational design domain, which includes environmental conditions such as weather or time of day, geographical conditions such as road features or terrain, and maneuvers, which means basically kind of like the road lanes or any types of instructions or signs that we have out there. And so some of the major factors or compositions of infrastructure that we found were designated truck lanes, smart corridors, pavement and pavement markings, road conditions, signage, and work zones. And put together along with the equipment, the autonomous truck equipment, you can kind of see like a picture like the one on the left that shows kind of how it all works together. And for this in particular, TTI was able to tour Aurora, which is one of the autonomous truck companies that's testing in I-45, and they have their center like an hour south of Dallas. And so we were able to ride that day on one of the trucks. And so this is an image from one of them, and it was a particularly rainy day too. So I thought it was really cool that you could see like the splashback on the image itself. So it's they're very sensitive machines. So you can see like the cars and some debris, the road signage, and also just the water. And here's an overview of the autonomous truck companies. We have more of them included in our actual literature review, but this is just kind of a highlight of some of the companies like Aurora, Kodiak Plus, and Torque, who focus mostly on long haul operations. And we have other companies as well, like Cruise or Gatic, that focus more on like regional or urban areas, and they focus on robot taxis or deliveries or business to business operations. And also too, initially, these companies are all operating along the Texas, not the Texas Sun Belt, but the U.S. Sun Belt area, so southernmost states, given that the weather tends to be more predictable and driving conditions are a little bit more manageable than up in the north. So here are a couple of preliminary findings from our literature review. There have been multiple legal policy and or regulatory changes, and so that means that there's states that are working on truck-only lanes, designated smart corridors. Some are looking into more lenient policy to kind of invite more autonomous truck testing or technology. But there's also been some more legal challenges as to whether or not we want autonomous trucks on our roads. So that's something that we're still looking into. There have also been recent guidelines released by the federal government that kind of includes autonomous technology into road design for lane markers or signage, which we're going to include in the final report as well. We also found that platooning is not really a priority for these companies at the moment, so there's still something that we might look into in the future. And then areas that still require attention are weather, work zones, first responder interactions, and data availability. And for this, when we talked to the Aurora folks, that's something that they mentioned, that weather and work zones were particularly some of the areas that they were still having issues with. And also, most recently too, we're expecting to see some initial commercial truck launches by later this year. So keeping my eye on that, seeing how things go. On to the survey. So once we completed the literature review, we broke down our questions according to general AVs, autonomous trucks and truck platoons, infrastructure, collaboration, challenges, and opportunities. And we also found different types of contexts that we would like to get their opinion on. So that included .staff, FHWA, AASHTO, TRB members, and other researchers, and most importantly, AV companies. And so on the right, you can see how we split up, or the share of contexts that we had, which most of them are comprised of state or municipal transportation, followed by AV companies. And we had like a total of, let's say, like 100 contacts in our list. So it was some work. And these are some of the highlights of our survey responses. We're still going through them, but the first thing to highlight was that to expect to see some commercial launches within the next month or two. For the next one, we will most likely see autonomous truck platooning within the next 5 years. That was one of the questions we had, since we weren't seeing lots on truck platooning. So we were wondering to gauge kind of where they expect to see some work on this happen. On average, AV truck companies operate 30 trucks. And this was also, after looking for truck tents online, there wasn't much on the total share of trucks that we expect to see over the next couple of years. So this was kind of to get like an initial view of like how many trucks are operating at the moment, since they mostly report trucks in the form of, or truck trips in the form of vehicles miles traveled. And so this will be important later on when we try to do like a economic analysis. And lastly, promoting information and data sharing, especially in situations where work conditions vary from the norm. That was one of the major takeaways from the survey responses. And that refers to specifically weather and work zones, since these companies they map their routes well in advance, and they do repeated tests from back and forth to the origin and destination, so they know kind of where they're going. And so, but once there's like a change there, sometimes they need that information, and it would help them a lot if they had more current information on the roads. And onto the more survey responses, and these are prioritizations. So we looked at adoption factors and opportunities, and we found that improving lane markers and sensor capabilities ranked highest, while truck lanes and transfer hubs ranked lower in priority. And then opportunities, mitigating driver shortage and improving safety were ranked the highest in terms of what autonomous truck technology can offer, while military use and lowering costs were not really something that we're aiming for at the moment. And on to the next steps, we're going to conduct the interviews and a peer exchange. So that's kind of where we're at the moment, and followed by guidance and recommendations for the final report. And expect to see that sometime late February or early March. And if you guys have any questions, I'm open. I feel like I had to rush.
I really appreciate you saving a little bit of time in here and keeping you to 12 minutes, 13 actually. Right. Thank you so much, Bill.
Thank you.
Any questions from the audience?
Can I have one, Claudia?
Yes, please, absolutely.
Bill, it's a great presentation. We have done some work for platoons too, but more on the impacts on the pavements, asphalt pavements. We have seen some interesting trends, basically how platoons may affect the pavement performance. But then I was reading a little bit about the trucking companies, and then are they still engaged and interested in adopting this technology? Because the main benefit for them is the fuel consumption, and to motivate them basically to adopt this technology. Are they seeing enough benefits to basically make an investment to be engaged in this type of operation?
I believe so at the moment. We'll learn more next year or so. But yeah, they've partnered with different fleet companies, and they're already making deliveries with a driver behind the wheel. But now, later this year, they're going to actually have driverless trucks on the roads. So yeah, that's kind of we have to see what the long-term effects of that is going to be, whether or not it's actually something that people want, since it's fairly restricted to the southernmost states. Like, is it something that can be expanded all the way to like the northernmost states as well? But yeah, about the truck platoons and pavement impacts, that would be interesting to read as well. Because I did talk to Jacqueline Cuso about that, and that's something that we were looking into.
All right. Great. Thank you, Bill. Thank you, Hasan. And any other questions from the audience? If not, thank you so much. I appreciate your participation in the colloquium. Our next presenter is Dr. Jobair Alam. Dr. Jobair serves as an assistant professor in the Department of Civil and Environmental Engineering at Prairie View, A&M University. Jobair specialized in geotechnical and geoenvironmental engineering with a proven track record in both industry and academia. His research interests primarily encompass transportation infrastructure, health monitoring, geophysical investigation, sustainable waste management, landfill cover hydrology, and data-driven methodologies, and earth infrastructure design. He has secured substantial research funding as a principal investigator and contributed to a wide range of funding research initiatives. And he has also published extensively in peer-reviewed journals and conferences, demonstrating a strong commitment to advancing knowledge in this field. So with all that said, welcome, Jobair, to the podium. Thank you for being here. We cannot hear you. You're muted.
Yeah.
Yes, and we cannot see your presentation mode. Okay.
Can you see it right now?
No, we see the normal, the PowerPoint without the presentation mode.
Is it okay now?
Yeah, no. If you want to present that way, it's fine, but we'll see your slides.
Jobair, go out of sharing and then go into presentation mode and then share, and it should work.
Yeah, you need to stop sharing first. Okay. So probably will be okay if Haley, if you share the presentation. Okay, yeah.
Just give me one more minute if I see if I can do it.
Okay. You got it. Thank you.
Is it visible
Yes.
now?
Yeah, go ahead. Now you have 5 minutes. Okay.
Thank you so much.
All right.
You so much.
Thank you.
Thank you, Dr. Claudia Zapata, for this nice introduction. And I will start my presentation with the topic, Smart IoT-based monitoring system of urban slopes. I am acting as the PI of this project, and we have Ahmed from Computer Science Department of Prairie View A&M University acting as the co-PI. And we have a couple of graduate and undergraduate students participated in this project. My presentation outline would be, first I will go over the basic literature and overview, and IoT overview, the objective of the study, the materials and methods, some data collection and preliminary results, and finally future research scope. So slope failure. So highway slope failures are a significant issue in the United States, impacting the nation's extensive road network and posing risks to both the infrastructure and public safety. These failures are caused by a combination of factors, including varied and often challenging geology or terrain, and highly variable rainfall or the environmental factors, and climate-driven extremes such as droughts followed by extreme rainfalls. The soil composition in the United States, in many parts of the US, especially the clay-rich soil, or often the researchers we call it expansive soil, also cause a significant threat to this slope failure. And the Texas is prominently known for this highly variable climatic conditions and clay-rich soil or the expansive soil. The two figures we see in this slide, those are the typical types of failure in Texas, where we have this clay-rich soil slope, where we have this shallow type of slope failure in the left figure, and we see a tension crack in the right figure, which can eventually lead to a catastrophic failure because of recurring swelling and shrinkage and easy movement of water through these cracks. Additionally, increased urbanization have changed the pattern of the drainage system of many slopes, and that also exacerbates the slope instability. So addressing these issues needs a multidisciplinary approach of geotechnical investigation and effective monitoring system so that the catastrophic failure or multi-million-dollar repair cost can be reduced. So impact of slope failure of landslides are many. They have significant social, economic, and environmental impacts. When a slope fails, it can cause partial to full road closures, and that can disrupt the traffic flow, inconveniencing the daily commuters and the transportation of goods. In terms of safety perspective, these landslides or the slope failure of highway embankments cause severe threat to the road users. The rock slides or the landslides or the collapse of soil from the slope can cause injuries, fatalities, or extreme conditions. And there have been many reports of fatalities and extreme injuries because of the highway slope embankment failure. And environmentally, slope failures often result in erosion and sedimentation problem, and that can cause problems with the local water body, and it can impact the local ecosystem. So that's why environmentally, socially, and economically, this landslides or the slope failure cause significant impact. Now, to reduce the impact of the slope failure, it's very important to monitor the slope physical behavior or the slope movement, time to time. But the challenges are many. So especially from complexity of terrain, especially in the state of Texas, we have variety of geological conditions and lack of diverse data collection system and analysis to make a informed decision making system, and of course the cost and resources and technological limitations and integration of diverse data to have a all-inclusive analytical system so that a early warning system can be developed based on the real-time data. So to address this challenge, Internet of Things or IoT can be a very good monitoring system. So IoT or the Internet of Things is a network of interconnected devices equipped with diverse sensors based on the need of the parameters to monitor, along with the different software and network connectivity that enable the system to collect, exchange, and analyze the data for instant decision making. The IoT can be a transforming slope monitoring by enabling real-time automated data collection system, which may enhance the real-time early warning system. IoT devices such as wireless network, rotational sensors or tilting sensors, inclinometers, strain gauge can continuously monitor the ground movement or on any vibrations on a slope. So these sensors transmit the data to over the internet to a centralized cloud system, and that informs the immediate remote access and data collection. And by detecting subtle changes in the slope, which may indicate the imminent slope failure or slope movement, this IoT-based system provides valuable insight for early warning and proactive maintenance of the slope. Now, this approaches not only reduces the need for frequent slope inspection, but also increases the accuracy and responsiveness of this slope monitoring system for better longevity and resilience of this infrastructure. So in this project funded by NSIDE, our objective was to develop a IoT-based monitoring system, including diverse types of sensors, from hydrologic sensors to physical movement of the slope using the tilt sensors or the tilt meters. And we conducted this study preliminary on the laboratory scale, and we developed a prototype model in the lab. And as we are doing this study in the state of Texas, and Texas is more vulnerable for its slope failure because of highly variable environmental condition, rainfall and temperature, and the existence of this expansive soil or this problematic soil. So we used fat clay, which is the more academic term, or expansive soil, to construct our prototype model. And the slope geometry produced is one vertical to one horizontal. We did it deliberately to make sure we can make this slope fail, and so that we can see if our system can detect a small amount of movement. And before the construction of the slope, we determined the soil's physical and mechanical properties in the lab. And during the construction of this prototype model, we compacted the soil based on the optimum moisture content of the soil, which was almost 17%. We used different types of sensors, as mentioned before. We used TEROS 11 moisture sensors and TEROS 21 tensiometers, which measures the negative pore water pressure of the soil suction into the soil. And we used a tilt meter or the tilt sensors to see how the rotation of the slope or how the movement of the slope is occurring. And later we tried to see how these hydrologic parameters and the slope movement combining together give us some decision-making parameters or decision-making idea. So our system architecture, we use different types of sensors as mentioned, and we developed the IoT gateway for the aggregation of the data and manage the devices connectivity. We use the Arduino board, which enables the Wi-Fi connection for the easy transmission of the data from the sensors to the cloud system. And we had two cloud systems to generate the hydrologic data and the slope movement data. So we use the IntraCloud system to store the hydrologic data, which is soil moisture and the soil negative pore water pressure. And we developed a ThinkSpeak, another cloud platform to store the slope movement data. And later, we actually aggregated both this system and developed one common platform where we have both the hydrologic and the soil movement data together. Now, this is our preliminary results from the development of our slope. We see that our Arduino board and the IoT gateway system is transmitting the data to the cloud, and from the cloud we can directly visualize the data, what is going on with the slope. We see also the hydrologic response. We can see we have some ups and downs in the soil moisture and the negative pore water pressure, and also we can see some variations in the slope movement. It's still in that preliminary level, but once we start our application of rainfall simulation, we will see more and more fluctuation in the slope movement and in the hydrologic data, which is soil moisture and the soil's negative pore water pressure. So the key innovations we tried to develop from this project is scalable and cost-effective monitoring system. As we know, nowadays we have different types of technology to monitor the infrastructure, but for slopes, especially failure-prone slopes, which often fails and takes DOT or maybe other DOTs, they spend millions of dollars to repair those slopes, recurring. So if we can use our methodology to monitor the slopes, so before any major failure occurs, we can see what's going on with the slopes and we can maintain the slope before the catastrophic failure. And definitely our cloud system or the IoT gateway system allow us to have the remote accessibility of the data, and we see what's going on in terms of the soil hydrology and also in terms of the soil movement. And also based on the real-time data, we can develop the early warning system and enhanced data integration. That means we can combine the soil hydrology and also the soil physical behavior, which is the movement or the rotation of the slope, and combine together, and that can give us a very important decision-making tool. So the outcomes until today, we could develop the slope model And we did the instrumentation, we developed our IoT gateway, and we developed the cloud system. And we also have developed a guided user interface and API, or the application programming interface, for the real-time data visualization. And we will improve that with time, but we are successful in developing the preliminary level API development. And a future research scope from this project, as we are collecting data, and we will continue collecting data, we will implement the machine learning model and try to predict the slope failure, imminent slope failure, based on the soil hydrologic behavior and the slope movement based on the rotational data. And also we will apply, we already have, have started applying some rainfall simulation, and we will have the rainfall and the environmental data, and also room temperature, or we will also simulate the temperature. And we'll have more and more data for the machine learning model to have a more robust prediction model. And we will also do the sensor calibration upon requirement. And we will also improve our user interface, where we will add more data to see a diverse data to have a very good idea about what's the condition of the slope. So broader impact of the research is enhanced infrastructure safety, and there definitely is a low-cost monitoring system. It can allow us some economic savings based on the implementation in the slopes, where there are variable climatic conditions and problematic soils exist. And also we can have a scalability and accessibility of remote data. Especially this will be important in terms of where there is a hard to reach slope. And if we can implement this technique, we may often or frequently observe what's going on with that slope, and we don't need to go to those hard to access slopes quite often. And of course, the IoT implementation in the geotechnical field is not that much as of now. So we're trying to also implement this IoT technique in geotechnical investigations, not only for the slopes, but also for any other infrastructure like pavements, dams, or levees, or any other infrastructure. So products to be used by end user at the end of this project, and we are very positive that IoT-based monitoring system, our system could be utilized by the authorities like Text DOT or maybe other DOTs, and we will have a user-friendly web interface for easy data visualization. And the real-time data can give us an early warning system for the slopes for proactive maintenance. And of course, a machine learning model can give us a very good insight about when we can expect a slope to fail, so that we can go to the site, and the authorities can go to the site and make some repair before that major failure occurs. So those are the things we are very positive to be implemented, and end users can be very much familiar with this our technology or our method. So far we have published one journal papers from this project, and we submitted 2 papers, one to the National Congress in Geotechnical Engineering, which is under the ASC, that has been accepted for publication and presentation. And also our project work has been accepted for presentation in the Transportation Research Board 2025 in Washington, D.C. And one more publication is under review under the IEEE International Conference on Computing, Networking, and Communications, ICNC 2025. And a few more publications are on the pipeline to be published by next semester. And we are very grateful to Insight for funding this research. And also we are grateful to PSI, Intertech PSI, for facilitating us collecting the soil from one of their project areas that helped us to collect the high plasticity clay soil or the expensive soil. And thank you so much for your patience.
Thank you, Jobair. I appreciate your presentation. Wonderful. Unfortunately, we don't have any questions time right now. And so if you need to reach out to Jobair, please do it on the private rooms during the colloquium. We have, last but not least, our presenter here is Dr. Surya Congress. He's an assistant professor of civil and environmental engineering at Michigan State University and an FAA certified drone pilot. His research uses uncrewed aerial vehicle photogrammetry and artificial intelligence to advance infrastructure inspection and management. Key interests include soil stabilization, sustainable geotechnical design, climate resilience, digital twins for structural health monitoring, and computer vision for real-world application. Dr. Congress has received funding from multiple agencies and served on several committees within the TRB and ASE. Outside work, he enjoys outdoor sports and glacier hikes. Welcome, Dr. Congress. I'm sorry about you being late for the next moderator system, but I guess we start late in here and we're just dragging it out. Please bear with me here. Thank you so much.
Sure. Thank you so much for the introduction, Dr. Zapata. I appreciate it. Sorry I couldn't join this meeting before because of my undergraduate class. So I'll try to be brief because I have another moderate session immediately. So I'll try to cut down my slides, which I normally don't do. But so I'm going to present our research work on asset management of bridges using uncrewed aerial vehicles and machine learning models. It's a collaborative project between Michigan State University and Texas A&M. These are our project collaborators. And thanks to consortium partners as well. So just to start with, bridges in the United States, there are roughly around 617K bridges, according to the 2021 ASC Infrastructure Report Card, and 42% of the bridges are over 50 years old, and 7.5% are in poor condition as well. So daily, 178 million trips are taken across these bridges. I mean, they are in poor condition doesn't mean we cannot travel, but they need more monitoring and maintenance. So we need novel technologies that can perform performance monitoring and also prediction. So that's the essence of the research that we conducted as part of this study. So if you can see, there is photogrammetry, which is a science of making measurements from 2 or more images, and you can accomplish it using smartphone cameras to sensor-mounted satellites, whether it is terrestrial or aerial. In our study, we are particularly focusing on the use of cameras mounted on uncrewed aerial vehicles. There are 2 types of uncrewed aerial vehicles. There is rotary wing and fixed wing, depending upon how they generate the lift. And we are particularly interested in examining the application of close-range photogrammetry. As you can see, photogrammetry is basically from sensor-mounted satellites to smartphone cameras. So there is a wide range. So we are mostly focusing on close-range photogrammetry, which deals with the distance between the sensor and the object being within 1,000 feet. So with that introduction, you can see these are typical, fixed wing on the left and rotary wing on this side. Typical types of UAVs, and we were using UAVs to monitor bridges all over the country in multiple states. As you can see, that's actually glacier water in Alaska, where we were able to do 360-degree bridge inspection. I'm not going to dwell deeper into it in essence of the time. So I'm going to show you the 3D model that was actually generated from the images. As you can see, it gives you a realistic view of what is in the field so that we can assess the condition and also perform maintenance as needed. So this is just a 360-degree, one of the bridges that we developed based on the methodology we developed for Alaska DOT. So now we are using those data to actually automatically extract information. As you can see, during the data collection part, we used a mix of both automated and manual flight missions, depending upon the stages. And then we developed, like you can see, the 3D models, and you can also refer to the papers I can share you as well. So we process the images to generate 3D models. So most of you might be familiar with LiDAR point cloud. So similar to that, photogrammetry can also generate very good 3D models as long as there is no vegetation involved. So we geometrically correct them, and then you can see the orthomosaics. So these orthomosaics are further used to detect cracks and anomalies. In the later slides, I I'll show some of the learning models that we have developed and extracting the information so that we can use it to build a digital twin. Why? Because a digital twin is a clone. A digital twin is not just a 3D model, but a clone where we have continuous feed of information so that we can predict how this infrastructure behaves in different conditions in the future. So that is the end goal. So with this introduction, let me show some of the work that we have been conducting on. So typically when you have bridge assets, there is road involved, there is multiple other structures and bridge elements involved. So what we are trying to do is our counterparts at Texas A&M are actually using pre-trained data sets from Massachusetts, which is available online, and they split into 256 by 256 tiles. Because when I say an orthomosaic, it's a big area, we cannot just straight away use it to train without pre-processing, because we only have limited computational resources. So we have to split that into tiles, and then we mask them and create a ground truth, and also divide it as certain percent into training and certain percent into validation, so that it's basically, I always give this example in my classes as well. Machine learning models or deep neural network models are basically like a kid. So when we teach a kid, hey, this is an apple, and you see an apple in the future, tell me that this is an apple. So that's how we are actually training the computer, basically giving them the ground truth, saying these are cracks, these are distresses, or this is road. Tell me in the future when you see that. So what is the advantage of this? Basically, if you have miles and miles of pavement networks or bridge networks, training process will take a lot of time, because we have a lot of learning rates and epochs, different iterations in learning. But the advantage is once you have developed those models, you can actually use them on most similar data to extract information very quickly. So that's one of the advantages, that you can scale it to a pavement network or infrastructure network. So as you can see on the right, this is the image and mask of the road created to train the model. And this is the training loss and validation. Basically, we would want it to be minimum, but also we don't want it to overfit as well. So based on experience, we identify an optimal epochs where we would like the model to be stopped. So again, if you're interested in learning any of those, feel free to reach out. But I'll just briefly give you the training loss and validation loss will be used to identify the best model. And here you can see the test image and the generated mask on the road, where you can incorporate this information into the BIM software, which I'll briefly talk in the next slide. So you can see this is semantic segmentation of roads. So in semantic segmentation, we can't still differentiate how many roads are there, how many feature classes are there. So we adopted instance segmentation for the distress identification for the work that we are doing currently at Michigan State. So as you can see, the same. Training process is same, but we are using a different deep neural network architecture. In fact, we are trying multiple of them so that we know which one works better. So the typical steps involved are, we provide ground truth, basically teaching the kid that it's an apple, and different learning rates, and also epochs are more like iterations that we put the batch together and train it. And thanks to our students as well, they spend so much time in building this and also iterating, because they won't work just like that. Because most of the models that you see online, they are basically trained upon apples or oranges with a clear background. But as a civil engineer, what you see is when you go into the field, a crack and a tire mark might have similar characteristics. I mean, as a person, but for a computer, unless we give more information, it still thinks the crack is same as a tire mark or a watermark. So those are the challenges that we as a civil engineers face, and we are able to solve them. And I will show you, this is the different tiles as well that we can use. As you can see, there is 256 by 256 and 128 by 128. I see Dr. Zapata switched on the camera, so I only have few minutes left, so I'll just move on to the last few slides. So as you can see, this is the original image where there is spalling on the bridge, as you can see. And this is a predicted mask. How well you can see we were able to predict. Now that we got this in the tile, we also inferenced it or detected it on the whole bridge in Alaska. Again, as you can see, there is so much spalling distress. So we were able to generate masks for all of them. So the advantage is you can actually automate this process. If not for this process, what do you need to do? You need to have the DoD personnel stop the traffic and measure it even subjectively. But here, we are getting as it is. Whatever is there, we are getting it. Let me show you a close-up view so that you can see. I would ask you to pick a distress. You don't need to tell me, go ahead and pick a distress, and then the next slide, I'll show you the detection so that you can see if your detection is, if your distress is there or not. So I assume you selected it. So you can see that's how good the neural network. But to get this, it takes a lot more effort and training. So with that, I would like to summarize our research. Using UAV CRP, we can conduct 360-degree bridge inspection to evaluate and visualize the condition of bridge infrastructure assets. And we can do timeline monitoring, like you do it now, 6 months, a year later. So you can do timeline monitoring to understand how the distress is progressing. And it's safe, quick, and efficient. Again, when we did the inspection, we did not even stop the traffic. We flew the drone, and then we didn't. We just collected within 30 to 40 minutes, and then we collected the data and processed it. And we can also use it for disaster response easily. And this approach will save 90% of storage requirements, and automation of condition assessments can be fed into Beam software, which is what we'll be working in the future, where we can conduct performance predictions as well. So with that, I would like to thank the NCIT organizers for giving me this opportunity. And thanks, Dr. Zapata.
Thank you so much, Surya. Appreciate your participation today. I have so many questions in here, but I guess we're going to have to do them on a private room in here. Thank you so much for all attending the session. And that, with that presentation from Dr. Congress, this technology sensor is concluded. Thank you very much.